Hi, this is Roger from Kanker Labs, and today it's about this audio signal tracer I got cheaply from eBay. It's another one from the, in Germany, famous ELV 7000 series, and I got a bundle of 4 different devices, all declared as non-working, but in fact they were all working and only needed a little bit adjustment. But this one here, I noticed 2 little issues, and over the weekend I analyzed the circuit. In fact, I already have one of these in my home lab, and in this and the next episode we'll discuss what the issues are coming from and how they can be fixed. But first of all, let me describe the features of this thing. This was not built as a precision measurement instrument, although it looks like one. It's designed for audio repair shops or the ambitioned hobby electronics guy. And so it's divided into an analyzing part and a generator. Let's start with the analyzer, which is the more interesting one. First of all, you can see it has 4 different inputs which are relay switched inside. You have your BNC input just for connecting an oscilloscope probe, 2 RCA jacks left and right, so you can quickly switch for comparing the level of left and right channel, and the venerable German or European DIN input. And as you can see, it can display at the same time the RMS level either in millivolts or volts, or automatically in dB. And the dB display can be switched between the reference level in dBm. dBm is defined as 1 milliwatt of power into a 600 ohm load. And if you do the math, that is exactly a voltage of 775 millivolts RMS. But you can also make relative measurements just by simply pushing the 0 dB switch, and then everything is referenced to your arbitrary level, and you can anytime switch back again to the dBm level. I hope you already can see the little LED for the minus sign. The input range is quite large. Here it's at the most sensitive level, which goes from 10 microvolts as the least significant digit or the resolution, up to 2.56 millivolts, and the highest level goes to 256 volts. So you can measure from the microvolt up to level up to line voltage. That's quite nice, and in auto-range mode there are all in all, I think, 6 modes, also relay switched, and the input circuitry is quite interesting. It's a 3-stage op-amp switchable amplifier stage. The input impedance is 100 kilo ohms in parallel to 100 picofarad. That is in fact nearly the optimum value you can realize with this circuitry. I couldn't get it any better, and we will also discuss later why this is the optimum. But you can see there's a little issue in the most sensitive range here. In the background you can see I'm just making a logarithmic frequency sweep from 20 Hz to 20 kilohertz. And you can see there's some little drop off here at the lower range, at the lower frequency, as well as at the higher frequencies. And we'll discuss where this comes from. This is much better in at least the high frequency fall off. This is better in the higher ranges. But when you have 0.1 dB resolution, what I would expect is a total error, a maximum total error of half a dB, because that's what you need when you're adjusting or checking audio circuitry, hi-fi amplifiers, etc. And it doesn't keep up with this. It's the error, as you can see here in the frequency sweep, is certainly larger. You can also watch the dB display that we have a total error of around 1 dB, and that's too much for me, but you can do something about this. So let's go on what comes behind the input amplifier stage. They really went to the effort to use at that time, very expensive True-RMS converter from Analog Devices, the 8636. So this is really True-RMS measurement. And what else do we have? You furthermore have, as you perhaps can hear in the background, you have an internal loudspeaker just to check the signal acoustically, and you even have an automatic volume control here, which you can switch off if you want to. The volume level, I'll turn it up a little bit, can be turned up here, and you also have a connection for, turn it down again, for an external loudspeaker up to 1.5 watts, or for headphones. And if you switch in either the external loudspeaker or the headphones, then the internal speaker is turned off. So, and what else you have is for checking the playback of vinyl records. If you change here what is here designed as impedance, if you switch this to magnet, that means there is a true record playback de-emphasis circuitry. So another quite nice feature. And I think that was it for the analyzing. So no, there's something else. If you push both the volts and millivolts range button, then you can make a quasi-power measurement. Let me push it again. First of all, you can set the impedance to values of 1.6 ohms, 2 ohms, 4 ohms, 5 ohms, 8 ohms, 16 ohms. And of course, this is not a true power meter. It just calculates the power by using Ohm's law. If we just square up the RMS voltage and divide it by the chosen impedance of your loudspeaker, then you get the display. And it displays the average value on one display and the peak momentary value on the other display. At the moment it's of course 0, 0, because the level of a few millivolts is so low that this is below the range that can be displayed. So pushing it back to level mode. So here we are back at level mode. And the generator circuit, first of all, it has 4 different frequencies, quartz generated with a distortion of less than 1%. And then you can see here you have 4 different outputs, the same as the inputs here, a B and C jack, 2 RCA jacks for left and right, and your DIN 5-pole jack. And what's also quite interesting, the output level as well the output impedance can be changed here by this little push button from 50 ohms output impedance and full level. Then you have a microphone output with a level around, I think, 10 millivolts maximum and 500 ohms output impedance. The auxiliary output has also full level but 100 kilo ohms output impedance. Magnet simulates with 47 kilo ohms and I think 100 millivolts output, a record playback system. And crystal means before moving magnet or moving coil pickups came out, there were in fact crystal or ceramic pickups used in record players. And this one here simulates the impedance and the level of a crystal or piezo pickup. But there is another issue I found which we will discuss in another episode if I find the time. And here you have a fine control for the output level, so all quite nicely designed. But as I told you, there are a few, or in fact two issues about the frequency response of the input stage and the output level and impedance of the output stage of the generator, frequency generator stage. And the rest of the circuit here you can see, I don't take this apart. You could see in the background some screenshots from the original manual or article in ELV magazines. This one here, there's the microprocessor, of course custom built with a custom ROM, and there is also an 8-bit ADC, because at that time, I think in 1990, there weren't any microcontrollers with an integrated ADC available, so they had to use an external one, the MUPD7001, as far as I remember. So that shall be it for a first look, and now let's take a closer look at the input stage. So this is the full measurement circuitry. It looks quite complicated at the moment, but let's go through it first in blocks, and then we take a look at the details. Now here are the 4 different input, the DIN jack in parallel with the left and right channel, the BNC input, and you can also switch the output of the generator directly to the input. And you can see some protection diodes, some resistor capacitor networks, and of course the 4 relay switches. Then comes the first amplifier stage here, and you already can notice that this is a compensated input stage because you always have a resistor and a capacitor in parallel, and it can be switched between amplifying and attenuating by switching on one of the relay contacts. For example, the first stage can switch between an amplification of times 10, times 1, times 0.1 and times 0.01, or a division ratio of, here in the last two stages, 1 in 100 and 1 in 10. So that's the nice feature, because the op-amp is used in the inverting mode, and there you can have at the same time amplification as well as attenuation just by changing the resistor. And they are using in the first stages the NE5532 out of the NE55 series. So this is a low noise, low distortion op-amp, quite a good choice. And then comes the second amplifier stage, coupled via an RC combination and a DC blocking capacitor, and again this time only 3 different amplifications, times 1, times 0.1 and times 0.01, or divided by 10 and divided by 100. So you also can see here which relay contact is switched depending on the range that you're in. And the third stage here is a simple TL081. You don't need any high-end amplifier here because the signal is already so high that you don't need a low noise. It's just coupled via here a DC blocking capacitor and the resistor going to ground just for the bias current. And this one here is used also to trim out any remaining offset voltages of the TL081. And next is the True-RMS converter, the 8636, and you can see some analog switches, the CD or CMOS 4066. The reason is we are measuring here at a very large frequency range, and if you've ever worked with one of these True-RMS converters, you will know you have an averaging capacitor which has to be dimensioned depending on the frequency that you're using. So the 1 microfarad averaging capacitor is used for the lower frequencies, especially to give exact measurements at 20 Hertz. And at the higher frequencies, the 100 nanofarad averaging capacitor is switched in. And the same is here with the output ripple filter. This is I think a 2-pole Butterworth filter, and there already the filter characteristic or the cutoff frequency is simply switched to 2 different values with the analog switches here. So this is nearly textbook-like. It follows exactly the design procedure in the application notes for the 8636, and you have an extra offset trimmer. And behind that comes again, which is not shown here, an amplifier of ×1 to give a final full-scale range of 2.56 volts, and that's exactly what goes into the ADC as full-scale voltage. But now let's take a closer look here at the input stage. So now let's take a look at an enlarged part of the input circuitry. What you first have to know is that an op-amp in the inverting configuration presents at the inverting input a so-called virtual ground, or the potential that your positive input is connected to, which usually is ground, like here. So what impedance does a source that you are probing, or any point in your circuit that you're probing, see? First of all, the signal goes through this 220 nanofarad big capacitor, which is rated for mains voltage. In Europe, 250 volts is the AC rating. This is first of all just for blocking any DC voltages, or to provide an AC coupling. And why does it have to be such a large value? And in fact, at this voltage it also is quite big. Well, because behind that we have our chain of resistors, and this of course is a high-pass filter. And what you want is, we will simulate this just in a minute with LT-Spice. You of course do not want any attenuation of 20 Hertz or low frequency signals by this high-pass filter. So you have to make this relatively big. Then the first resistor that comes, this is simply a current limiting resistor, because if you connect your probe to a high voltage source, then at the very first microsecond your capacitor will behave like a short, and that could mean that there would be a very high current flowing through the input capacitor, and then through this little 100 picofarad capacitor, and then into the input of your op-amp. Now, the datasheet of the NE5532 says that you have to limit the current into any input to a maximum of 20 milliamps. Now, if you do the math, if you would really connect mains voltage of, let's say, 230 volts through a 2.2K resistor, you would in fact get around 100 milliamps. Now, shouldn't this be then any bigger? No, because the total energy that can pass through this little 100 picofarad capacitor on its way here through the relay contact to the inverting input, the energy is so small that your input won't be destroyed, because in the end it's neither voltage nor current that destroys your semiconductor. It's the energy that you put into your semiconductor in a certain period of time. And if you limit the energy that can at maximum be fed into the input transistor of your op-amp, then you won't destroy it. So this combination is quite okay. This would be the topic of another episode, because there are many misconceptions what really destroys semiconductors. As I told you, it's not voltage, it's not current, it's the energy in a certain amount of time. So this is quite okay. And then comes a chain of 3 33K resistors. Now you may ask, why didn't they put a single 100K resistor? Well, quite easy. Resistors are usually rated only for between 100 volts DC and 250 volts DC, but a maximum input voltage of 250 volts AC is has nearly a peak voltage of 400 volts. So one single resistor can, in theory, not withstand a standard little quarter watt resistor cannot withstand 400 volts DC peak voltage. So that's what you usually do. You divide your input resistor into 2 or 3 single resistors, so that at every resistor there's a maximum of 100, in our case 130 volts around. So it's not important that if you add up the total resistance, you get 99K plus 2.2K. That gives 101.2K. It's not important here to have exactly 100K input impedance, simply because you can trim out either by hardware or by software the true scale factor of your whole circuit at a later stage, so it only has to be somewhere around 100K. And then we have 2 little anti-parallel protection diodes, just to get away with any overvoltages at this point. And this is the right topology to protect the input of an op-amp in the inverting configuration. You might have seen my video about input protection, but there we took as an example an op-amp in the non-inverting configuration, and there the protection diodes are placed differently. Here, that's exactly how you do it. 2 anti-parallel diodes, so that the voltage at this point can never get higher than 0.7 volts if you use silicon diodes. So, and now you may wonder, why do you have to have this 100 picofarad capacitor, and then in the feedback connection this 10p capacitor? Well, that's what you call a compensated voltage divider. You should know that in the inverting configuration, the gain of your first op-amp stage is simply the value of this resistor divided by the value of the chain of these 4 resistors. So we have nearly 1 megohm divided by 101.2K is nearly a factor of 10. And you already can notice also the two capacitors have a factor of 10, but in the reverse order. Here we have the high resistor in the feedback loop and the low capacitor, low value capacitor. And here in front of the inverting input we have the low value resistor chain and the high value capacitor. So we will simulate this with LT-Spice to give you an idea why this configuration is used. So from the first amplifier, the signal is routed to the second inverting amplifier. Here in the configuration again with a gain factor of 10, we see our, in this case, our 10K resistor in parallel with a 1 nanofarad capacitor and a 100K feedback resistor, and the ratio 100K to 10K gives of course a gain of 10, and in parallel a 100 picofarad capacitor. And between the two there is still this AC coupling capacitor of 1 microfarad, and this is just to remove any offset voltages here from the first amplifier. And already here you can guess there could be a little issue with the choice of the value of this capacitor, but we will discuss this later. So now let's try to simulate if we can see the little drop-off at the low and high frequency by simulating the total input stage of the 3 op-amps. The third one here is simply a unity gain buffer with a 1 microfarad coupling capacitor. And we will do this for the whole frequency range from 20 Hz to 20 kHz. But we will do a stepped analysis. We're stepping the impedance of the source that we are probing. So you do this by giving the variable that you want to step a name. Here we are just stepping the series resistance of our voltage source, and you put the variable name between curly brackets, and this is the step command. It's quite easy. You determine the name of the parameter or the variable that you want to step. We make a decade sweep because we simply want to step up our input impedance by a factor of 10, starting from 1 kilo ohm up to 1 meg ohm, and the number of points per decade is then of course 1. So we get 1 trace for 1 kilo ohm, 1 trace for 10 kilo ohm, for 100 kilo ohm, and for 1 meg ohm. And let's do the simulation and see what we get. And we do have here already the drop-off at the lower frequency range. And what's quite strange is if you increase the input impedance of the source that you're probing, you get a different fall off at the higher frequencies, and of course you get different values of your level, of the dB level. That is simply because your input impedance here, which is of course the output impedance or the series resistance of our source, forms a voltage divider. Let's suppose we would have 1 meg ohm, then we would of course have 1 meg ohm, and here rounded 100K, so this gives a 10 to 1 resistor divider, and we would expect that the 1 meg ohm value is around a factor of 10 or 20 dB lower, and we see our first curve with 1 kilo ohm impedance is at around 40 dB, and the 1 meg ohm is nearly exactly 20 dBs or a factor of 10 lower. But what's quite strange is the different behavior of the fall-offs. You can see here at the high impedance source, there's a little bit less fall-off than here, but in contrast to that, we have a higher fall-off at the higher frequencies. So at the first moment, quite strange, but we will explain how this comes and how you can counteract this behavior in our next simulation, where we start step by step from the very first input stage. So here we have an extremely simplified first input stage or first amplifier stage. You might notice I've left out the parallel capacitors here just to demonstrate later what they are good for. And the 4 input resistors in series, I've added them up to a round value of 100K. And you might notice now we have 150 nanofarads of the value of the coupling capacitor. That is because in the parts list of the real device, there is 150 nanofarads noted instead of 220 nano. That is given in the circuit diagram. The reason might be that at that time, in the right shape and not too big, they only got a 150 nanofarad rated for 250 volts AC. And now let's first see what we get. Again, we step the input impedance of our source, or to be correct, the output impedance of our source, from 1 kilo ohm to 1 meg ohm. And let's see what we get. And we get nearly a linear frequency response, so we have no perceptible roll-off or fall-off at the high frequency, but we do observe here the fall-off at the low frequency range. And this is also dependent on the impedance of our source. So the 1 meg ohm source gives a flat response, but when we probe low impedance sources, then we get a fall off in the range of from 19.8 down to 18.9. This is around nearly 1 dB. And this is clearly too much. And this must be simply from the impedance here of this capacitor. Now let's just see if we change this to 470 nano, if it gets any better. And it is. Now it's nearly perfectly linear or flat. The fall off now is below 0.1 dB, so that's what we need, and this is a simply remedy or bug fix. We just have to use a bigger input coupling capacitor. Now, why did they choose only 220 nano or in the end 150 nano? This was simply a choice of the available sizes at that time, nearly 30 years ago, and they wanted to have this 100K input impedance for the input resistor, and the best they could get is 150 or 220 nano. So now we don't observe if we go back to full extent, so that would be a nearly ideal flat frequency response. The question is, where did this high frequency fall off at the real circuit come from, and why are they using these parallel capacitors? Now the reason is quite simple. You always have some stray capacitance, especially here. Let's say we add a capacitor of only, which is just the parasitic capacitance just of your PCB traces, etc. of just, whoops, it's gone again, of 2 picofarad. Let's connect this and see what happens. Let's give it a value of 2 picofarad and simulate again. And we already can observe here we have this little roll-off. Let's see how large it is. We're going down from 19.9 dB to 19.6 dB. So this is already a 0.3 dB roll-off or fall-off. And if you remember, we had 3 stages. So if we have 3 times this behavior, this adds up and in the end gives 1 dB or more fall off at the high frequency range. So what do you do just to compensate these stray capacitance? Well, you choose a resistor much larger and at best trimmable in parallel to this stray capacitance, and then you place, just as the ratio of the feedback resistor or of the input to input resistors here, you place a second capacitors in reverse proportion to this 2 resistors here in parallel to your input resistor. So let's choose exactly the values that they did, 10p plus 100p here, because our 1 mech resistor and our 100k resistor have a ratio of 1 in 10, and the 2 capacitors also have this ratio but in reverse order. And let's see what we get in an ideal world. And you can see now here the response now is nearly absolutely flat. We have only this 0.1 dB fall off here caused by the 470 nanofarad. If you would enlarge this to 1 microfarad, which is physically too large in practice, we will even get rid of that, and at the 1K impedance we have an absolutely flat response. We have a very slight fall off here, also in the range of slightly less than 0.1 dB, so absolutely sufficient. But here at 100k and 1 mech ohm, the fall off becomes larger. So this would be a good compromise for measuring impedances up to 10 kilo ohms, but from 100 kilo ohm onwards we still get a slight fall off. Here it's already 1.5 dB, and if we probe a 1 mech ohm source, we have a fall off in the range of from -1 to -3 dB. So you just have to be aware of that the level you measure as well as the frequency response depends on the impedance of your source. That's a very important thing to remember. Now there's still one thing that could be improved. If you are using a 10p capacitor, of course first of all you have a tolerance of at least 10%. That means it could be anywhere between 9p and 11p, and you still have your 2 picofarad stray capacitance. So the worst case is this could be in fact summed up with a stray capacitance. This could be 13 8p. And what do we get then? Well, gone is our flat frequency response. Now we already have at our 1K impedance, we already have from 19.8 down to 18.3. We have more than 1 dB loss of level. What would you do to get away with that? You make this, of course, a trimmable capacitor. For example, you take an 8p capacitor and use a second variable capacitor. I don't have the component symbol here loaded, so just think of that as a fixed capacitor and then again a trimmable capacitor. And that's exactly what you do with your oscilloscope probe. You know that your oscilloscope probe has a little capacitance trimmer which has exactly the same purpose to give an exact compensation. And now you know why this is called a compensated voltage divider, because if the ratio of the true, including stray capacitance, of the true capacitors, of the true values of the capacitors is in exact reverse proportion to the values of your voltage divider, then you would get a perfectly flat response at the high frequencies. And at the low frequencies, this is only limited by the value of this capacitor in relation, of course, to your 100K. So that is the main reason why you use these voltage dividers with parallel capacitors. But what they did wrong is they should have made this 10p capacitor trimmable. If we again take a look at the total input circuitry of the first two stages, you may notice all the other gain factors that can be set with the relays, they have much larger capacitance. So here at these gain settings, the stray capacitance doesn't come into play. But here at the most demanding stage and at the most demanding levels where you measure in the millivolts or microvolts range, there you have to have a 10p capacitor, and there 1 or 2 picofarad stray capacitance are really important. In the second stage, the demands are very much released, because here then we have 1 nanofarad and 100 picofarad at minimum value. So here stray capacitance is of no importance. You wouldn't need an extra capacitance trimmer here in parallel. But here it would have been a very good idea to use a combination of an 8p capacitor plus a little capacitance trimmer. So that already has explained at least part of the high frequency fall off and part of the low frequency fall off. But the low frequency fall off does not only come from the first capacitor. Remember, here we have a second one, and if we look at the full circuit, then we can see we have our first low frequency limiting capacitor here. The second one is here, this 1 microfarad, and again a third one is here, 1 microfarad. And in total we saw this did give more than 1 dB fall off. So if we increase all three of them, this one here to 470 nanofarad and the two 1 microfarad capacitors, we simply enlarge them to be on the safe side to 10 microfarad. So let's see what happens then. So here we are back at the full 3-stage input, and we already said we want to change C1 to 470 nano, C5 to 10 microfarad, and this one also to 10 microfarad. And let's see which frequency response we get now. And we're probing again at the output of the third op amp. Let's get away with we don't need the face. And this looks much, much better. Up to 10 kilo ohms output impedance of our probed circuit. The low frequency fall off is nearly, not quite, but nearly negligible. It goes down from here from 39.8 to 39.6, so that's 0.2 dB. That's absolutely tolerable. And the high frequency roll-off or fall-off is still less. But what remains is you have to be aware, probing a 100 kilo ohms source or even a 1 megohm source, you have to know you still have a substantial fall off in the high frequencies. Here at the 1 megohm source we get from 18.9 dB down to 15.4, so that's still minus 3 dB. And here we are down from 33.8 down to 32.3. That's 1.5 dB. Of course, you don't very often encounter sources that you're probing with such high impedances, like 100K or 1 megohm. But for example, ceramic or piezo stereo or mono record pickups, they do present such a high impedance. And this will be the topic of another episode, DIN sources. So not the low impedance sources that you know from your RCA connectors, but when you're using sources that are coming from a DIN connection, in the early days, like between the 1930s and the 1960s, these could in fact have an impedance of between 470K and 2 megohm. And then what you measure at the high frequency range does not give you the true values. So you might be fooled by thinking or by measuring with your audio signal tracer, well, there's a high frequency fall off, but this is simply due to the input circuitry that you're just probing with 100K in parallel to 100 picofarad. That gives this high frequency roll off, because the 100 picofarad here, they present a substantial load if you're probing a high impedance source. So thanks for watching. If you liked it, please give it a big thumbs up. You can support me on Patreon if you want to, and see you next time. Bye from Roger, bye from Kanka Labs.